Today we're going to explore a pretty interesting limit which was suggested by a viewer. And that's the limit as xy goes to the origin of x over x plus y to the n. Maybe the interesting thing about this limit is not actually the limit itself, although that's pretty interesting. The most interesting thing here is that Wolfram alpha says that the limit does not exist for n equals 1, 2, 3, and 4, but the limit is equal to 1 for all n bigger than or equal to 5. Of course, you can't really check it in Wolfram alpha for all n bigger than or equal to 5, but if you plug in lots of values of n, you'll see that you'll always get a value of 1 from Wolfram alpha for those values. So what I want to do here is maybe come to grips with, is Wolfram alpha correct or not in this case? What's special between 4 and 5 that makes this flip over, if it does flip over? And then maybe present like a bigger question, which I don't really know the answer to. Okay, so let's explore this limit algebraically first. So let's recall that this multivariable limit exists if and only if we can take any approach curve to 0, 0 and get the same value. So all we really need to do is check this upon a couple of different approach curves to see that we actually get different values. Okay, so let's do that. So let's first take the approach curve y equals 0. So let's see, y equals 0 would be like approaching along the x-axis. So that would be like doing this approach right here to the origin. Okay, so in that case, our limit will collapse to the limit as x goes to 0 of x over x plus 0 to the n, which is the same thing as the limit as x approaches 0 of x over x, which is equal to 1, because x over x is equal to 1. Okay, well, notice this didn't depend on the value of n. We got a value of 1 all of the time here, which seems to contradict this Wolfram alpha result for n equals 1, 2, 3, 4. Okay, so now let's go in along another curve. Let's say we're going along the curve x equals y to the n now. Okay, so what does that look like? Well, it really depends on if n is even or odd. Maybe I'll look at the case when n is even in orange, and maybe the case when n is odd in blue. So if n is even, we know that it's like a sideward facing something like a parabola. Great, so if we're approaching the origin, we're approaching like that. But then if n is odd, it's gonna be like something like this. So this would be n is odd, and again, we're approaching the origin. But we can work both of these cases at the same time. Okay, so in each of these cases, our limit collapses to the limit as y goes to 0 of y to the n over y to the n plus y to the n. Okay, but that's clearly equal to the limit as y approaches 0 of y to the n over 2 times y to the n, which is equal to a half. But, clearly, we know that the number 1 is not equal to the number half. So that means we've exhibited two different limits depending on which curve we approach the origin by. So this kind of finishes off this whole calculation and says, for all n, which is a natural number, this limit does not exist. So now let's look back here at what Wolfram alpha said. So Wolfram alpha got it correct for the case when n is 1, 2, 3, or 4, but it got it incorrect in the case when n was bigger than or equal to 5. So the first thing that I did after I noticed that Wolfram alpha was incorrect here, based off of my calculation, is that I calculated this limit in Mathematica just to see if Mathematica, which is also a Wolfram product, would make the same mistake. And in fact, Mathematica got it right. So I made a big table of all values of this limit, or not all values of this limit, but a bunch of values for this limit, and it found that the limit did not exist for lots of values of this limit, for lots of values of n, I should say. So the deeper question here, which is what I'm opening to you, is what kind of calculation is wolfram alpha doing that's incorrect in this case, that Mathematica is doing correctly? In other words, why does Mathematica get it right but wolfram alpha does not? So maybe if you know the answer to this, post it in the comments. And that's a good place to stop.